Now, for stars that have a mass which is greater than 1.5 times the mass of our sun, so that's what this here is, these stars, towards the end of their life, because these are the really massive stars, they're burning their fuel really quickly, they've got a lot of stuff inside them, but when they get towards the end of their life, they can supernova. Now, this limit here is called the Chandrasekhar limit. And there are two main types of supernova. Now, the first one I'm going to talk about actually is the type 2. Now, this is our kind of normal kind of supernova where it's part of the normal life cycle of the star. Now, basically, if this is our big star, towards the end of its life, it's running out of fuel, and that means the radiation pressure, keeping it kind of sort of as it is, in equilibrium at this time, that the fuel runs out, and therefore there's less pressure acting out. But yet the pressure inwards due to gravity, or the force inwards due to gravity, remains. And what happens is when it starts, when the fusion stops happening, the whole thing then starts to collapse, and it collapses at up to like 30% the speed of light. Now, when this happens, a couple of things occur. In the centre, you've got the protons and the electrons, which are kind of there. And basically, these things here are combined together because, that everything's getting smaller, they're pushed in. And that means that protons and electrons make a load of neutrons. And in order to conserve like lepton number, this also gives out a load of these electron neutrinos. So first of all, as this thing is all collapsing, you get a sudden huge amount of neutrons being produced. And often we can detect this kind of flux of neutrons before we actually see the supernova itself. The neutrons which are left behind can then make a neutron star. Now, the other thing that happens is that because as everything gets smaller, the temperature rises, this then causes a lot of fusion with helium rather than hydrogen. And this is called a helium flash. And basically, you've got two things. You've got the outer layers kind of collapsing towards the middle. You've got this then increase in temperature and this helium kind of flash in the middle. And this basically blows the outer layers away. And as this is all happening, the outer layers are also, kind of causing things to fuse to make really heavy elements. So we're talking about things which are bigger than iron. And you should be familiar with this diagram of the binding energy per nucleon. But basically, all of the elements on this side over here, these are formed in a supernova, and it's the fusion together of heavy elements, and that's where we get the stuff on Earth. The stuff inside my hands here and inside you watching this, the heavy elements can only have been made in one of these supernovas. But there's another type, which is called a type 1a supernova. Now, this occurs in a slightly different way, and it occurs in a binary star system. Now, in a binary star system, there are two stars which orbit like a common centre, and actually they're quite common. But basically, if you have a certain scenario where you've got maybe one white dwarf, so maybe a low-mass star that's ended up as a white dwarf, and this is next to a red giant, and again, these two things are both rotating. But basically, as this kind of becomes a red giant, some of the atmosphere can basically be trapped, or basically gravity kind of pulls it from the red giant into the white dwarf. And that means that slowly and slowly, the mass of the white dwarf gets bigger and bigger. Now, we can see there's going to be a point where if the mass keeps getting bigger and bigger, it might get above 1.4 solar masses. The mass of this kind of white dwarf star might reach the Chandrasekhar limit. And because of that, it means that the mass of this thing here is equal to 1.4 solar masses. Not like this one here. This could have a mass, which could be maybe 5 solar masses, because it could be any value depending on the size of the star. This one only occurs at this value. And that means that when we see the centre of this get to this limit here, what happens is that fusion happens again, and this then causes this white dwarf to kind of basically have this supernova. Now, in this supernova, because it suddenly gets really hot, what happens is that in the middle, there's fusion, and a lot of this fusion makes nickel 56. And this thing here is an unstable isotope. In fact, it's only got a half-life of about 6 days, and then it becomes cobalt 56, again an unstable isotope, which this one has a half-life of about 77 days. And eventually, it then decays to make the more stable iron 56, the kind of the most stable element that we have up here at the top of this diagram. And for that reason, because it always happens at this mass, it not only gives out a certain amount of light, and therefore we can actually, we know how bright it's going to be. It's its absolute magnitude, but also the light it gives out has a certain distinct curve, which I'm just going to draw down here. Now, supernovas are really bright, and therefore they're easily seen, or not easily seen, but they are seen by astronomers using our kind of amazing telescopes nowadays. And basically, if the light sort of increases and then decreases in this pattern here, we've basically got a little curve at the top here, which is due to the nickel, and then that decays, pretty quickly. And then what we see is another curve for the light emitted by that supernova as the cobalt starts to decay to make the iron. Now, for that reason, they've got not only a very distinguished kind of light curve, but these things also happen with, a kind of a fixed apparent magnitude, which I'm going to call big M here. So this is the apparent magnitude. Now, the important thing is that if we know how bright it actually is, and we also record how bright it actually appears to be, this is the apparent magnitude, we can then use the equation that links absolute, apparent, and the distance. And you can then work out the distance to these far off galaxies. And this is what we call a standard candle. So a standard candle in astronomy is basically something where we know exactly how bright it is. And if we know how bright it is and how bright it appears, we can then work out how far away it is. So that's just a little summary of the two main sorts of supernova, a type 1a, which is this kind of distinctive one from a binary star system and this distinctive light curve, and a type 2 supernova, which is formed when a massive star gets to the end of its life and it collapses. And again, with this one here, if it's particularly massive to begin with, whatever's left in the middle, the neutron star might eventually collapse in on itself again and make a black hole. So thanks for watching. Hope it all goes well.